Today we look at how floating point numbers are represented in computer memory. In the last episode we looked at integer representation in memory. It encodes integers precisely, but has two big limitations. One, it cannot efficiently represent very large numbers. And two, it cannot represent fractions. Floating point solves those two issues by sacrificing precision. Let's take a look at how it works. The smallest floating point number takes up 32 bits. For ease of demonstration, we'll use an 8-bit encoding as an example. We can approximate, and if we're lucky, precisely represent a real number by breaking it down to the sum of several numbers. As an example, positive 1.25 can be written as the following. Note we can rewrite those numbers in powers of 2. We can further convert them to multiples of 1/8. Now look at this number. Notice the three components that we need to uniquely identify this number. Its sign, its numerator, and its denominator. This encoding is called floating point because you can effectively alter the position of the radix point by increasing or decreasing the denominator, thereby trading between precision and size. So we encode those three components and job done, right? Not quite. Part of the job of any computer scientist is to make simple things delightfully cryptic. As a result, the actual rules for encoding are slightly more complex than that. If the number is not 0, or not very close to 0, then it is a normalized value. In this case, encoding uses this formula. This value is the exponent bias. Together with the value in the exponent field, we have the exponent value. This is the significand. This whole formula might look a little unpleasant now, but let's take a look at one example. Note, in our memory representation, the address grows from right to left. We partition those 8 bits into 3 fields: the sign bit, the exponent field, and the fraction field. The sign bit encodes the sign of the number directly, 0 for positive and 1 for negative. The exponent field contains an unsigned integer. For normalized floating point, it cannot be all ones or all zeros, but it can be any value in between. We'll see why in a moment. The fraction field contains an unsigned integer between 0 and 7, both inclusive. Suppose we're given this floating point number and we need to compute the decimal value. Let's use the formula we saw earlier. Since the sign bit is 0, it's a positive number. The value in the exponent field is 7. The exponent field has 4 bits. The value in the fraction field is 2. The fraction field has 3 bits. We find that this represents 1.25. If the number is 0 or very close to 0, then it is a denormalized value. In this case, encoding uses this formula. Similar to normalized values, this is the exponent bias. This whole thing is the exponent, and this is the significand. Suppose we're given this floating point number and we need to compute the decimal value. The sign bit is 0, it's a positive number. The exponent field has 4 bits. The value in a fraction field is 7. The fraction field has 3 bits. We find that this represents 7 over 512, which is approximately 0.013. If the number being encoded is infinity or is not a number, then the encoding is special. In this case, the exponent field contains all ones. When a fraction field contains only zeros, then the resulting value represents infinity. The sign bit is still used to indicate positive or negative infinity. When a fraction field contains any number other than 0, then the resulting value represents not a number. This can happen if you ask the computer to produce a result that cannot be represented in any other floating point form, such as taking the square root of negative numbers, or doing nonsensical computations such as infinity minus infinity. Real-life floating point encodings are a lot longer than 8 bits per number. You can see from this table the example we have been using thus far and everything that has been defined by IEEE 754. C implements single and double precision on all platforms. You might have noticed that floating point encoding cannot represent many numbers precisely. Those values are approximated using rounding, which we'll discuss in a future episode. Thanks for watching. I'd like to give special thanks to Mechanical Keyboards, who did not sponsor this video. Mechanical Keyboards give you digital orgasms. This is an Indian Tribe production, all rights very much reserved.